out. Don't have your friend do them for you or for you make a photocopy, handwritten by you. We are going to collect those ones. So when we are going to collect the exam, we have to put them back onto the file. In order that you can attribute them on those note sheets, please have written your code name. On the exam, you will only write your code name, nothing else. We are going to scan the exams and upload them just like we upload on this touch. So you will not get the physical copy of the exam. There will be one scan file with all 50 exams in a big PDF file, and you can look through that and see everybody's exam and that, including yours. That's why they show their code names. Are there any more questions about it? I expect you'll have about 45 minutes, 50 minutes for the session, and then 5 minutes in recess. We'll get you situated over this. Greatest peril in the exam is time management. Make sure that you know everything by heart, so that's quick to do. And if you get stuck somewhere, don't. Just go on. There will be, as you can see on iLearn, in the old exams, they are graded out of 100 points, but you can get like 110 points or 120 points or so in that exam. So you don't need all the points to get an A class. So even with 10% wrong, you still can get an A class, or 10% still, you can still get an A class. So don't fixate on one problem if it's hard for you. Just move on. Okay, any questions? I call this a practice exam because I expect that typically in the class, half of the students get an F on the practice exam. And that's just the way it is. And then there comes the real midterm, and students do much better on that. And then I'll take the better of the 2 grades, the practice of the real midterm. So the bad grade is move on. That's practice. Any questions? Okay, if that's not the case, let's quickly do this one over here. Just so that I'm sure you are still keenest aware on electric energy. If a lithium ion travels from a location at a potential of 0 volt to a location at a potential of -1 volt, how much energy did it gain or lose? That's correct. Did you not register yet?
I did. I've already done previous ones, so I don't be logging.
Okay, I'm so sorry for that. You can see it worked for 43 people at this point here. I'm not sure what is going on with you guys. I think we are now at 45 people, which is about the number of people we have in class. So let's go on and have a look at your results over here. And that should log it now. And 54% of you, of course, are correct. That is why we like electron volts. If we have one fundamental charge, like the lithium 1 plus ion, lithium is always a 1 plus ion, if we know what the lithium ion is, then 1 plus. If that is by 1 volt, one electron charged by 1 volt gives 1 electron volt. That is why electron volt is so handy. And no, it's not joules. It would be nice if joules or joules per mole would work like that. But they don't, and hence people use electron volts and not joules, if they think about it. But of course, joules is the SI unit. Okay, that's all kind of just a quick reminder. Then, last time, and the 2 last times, we really talked about temperature. And we're realizing that the temperature and the kinetic energy have a lot to do with each other. That we have 1/2 K Boltzmann times T, with K Boltzmann here being just the gas constant R 8.3 so-and-so divided by the Avogadro constant 6 to the 2030. Then that's times T. So we have for the kinetic energy in one direction 1/2 K Boltzmann times T. And then, of course, there's the same average kinetic energy in this direction and in that direction, so it's 3/2 K Boltzmann times T. So in other words, you can say atoms or molecules in the gas phase have 3 degrees of freedom. They can go in this direction, they can go in this direction, they can go in this direction. And for each degree of freedom, they have, on average, an energy of 1/2 K Boltzmann times T. And this concept, you have an energy of 1/2 K Boltzmann times T per degree of freedom, is something really fundamental, something you have to carry with yourself as a fundamental approximation how much energy is there in systems. Now, you have K Boltzmann times T if you think about one atom or one molecule. You have R times T if you think about a mole of that. So 1/2 RT is the average kinetic energy of a mole of molecules in X direction. And 3/2 RT, the R being the gas constant, is the average kinetic energy total in all directions of a mole of molecules. Then we talked about distribution functions, and we realized distribution functions are closely related to probabilities, but they aren't just the same thing. They aren't the same thing because they can be bigger than 1, for instance. Probabilities can't get bigger. But distribution functions can get bigger than 1 if they do it over a very short interval. So that the integral between, for instance, 2 velocities is much shorter than 1, then its g can be more than 1 and the integral is still less than 1. And then so it would work out. And then we looked at 2 particular distribution functions the last time. One was the one which we can derive without knowing anything about gas particles. And as a consequence, we call it the normal distribution, the one which comes out if we don't know anything about the system. And the first person realizing that was Mr. Gauss, and so it's also the Gaussian distribution. And it looks like that. Also people call it the bell curve for obvious reasons. And we realize this is a distribution function, meaning the whole thing needs to be normalized. So if it's wider, it needs to be lower as well. It's narrower, it needs to be taller. So that the integral over the whole thing always will be 1. Note that here it's 10 to the 3 multiplied over here. So if it's above 1, it's really only above 0.001. Okay. Now temperature, we realize, makes the whole thing wider. What I have in my distribution function is 1/2 mv squared, the kinetic energy in direction I, 1/2 mv squared, divided by kT, kT if I'm thinking about one molecule, or RT if the mass here is a molar mass and I'm thinking about a mole of molecules. Either way it will work, it's just expanding the whole thing with Avogadro constant. And then here again I have the m and the kT over here. This one here makes it shallower or taller, and this one here makes it wider or narrower. And of course this function is symmetric. I have the same probability for gas particles to move at that speed in this direction or in that direction. Then, and now we're getting a little bit to your homework, I can ask myself, what is the most probable velocity in x direction? MP, most probable. And of course that is no velocity in x direction. The maximum of this curve is at 0, so the most probable velocity for a gas particle in this room in x direction is that it doesn't move in x direction. I can also ask myself, what is the average velocity in x direction for gas particles? Now, what's the average velocity in x direction for the gas particle? It's of course 0 as well. There's no wind in this room. Wind would mean we would have the gas particles on average move in some direction, but there's no wind in this room, so there are just as many gas particles moving in this direction as in that, and so it cancels each other out. If you had looked in your homework on a freeway and counted the cars going to Moreno Valley and counted the cars going to Riverside, then the average of that, at least on a good day and so on, might have cancelled out as well. But with the cars, it's often there are more cars going in one direction than the other. There is a net flux, of course, cars in one direction. With gas in this room, it's not, unless there's wind. Okay. But if I'm asking myself, what is the RMS, the root mean square, which is another way of expressing an average, mean average, same thing, correct? So I take the root of the average of the squares, root mean square. If I'm taking the root mean square average, then I'm squaring the negative numbers, they become positive, the squares. I'm squaring the positive numbers, they stay positive, the squares. So now there is no averaging minus against plus anymore, it's all pluses. So now everything counts in a way, and the RMS velocity in x direction as a consequence is an appreciable number, it's not 0. And that is the same concept which you looked at in your homework. That if I'm taking the average of the velocity of the cars and then calculating the kinetic energy from that, or if I'm calculating the kinetic energies for each of the cars and then averaging them, one was the direct average here, and the other is the root mean square average which you did for. Because in order to get to the kinetic energy, you needed to square the velocity. So you have a square, and you make the mean after the square, and not the square after the mean. And as a consequence, you get different values. If you use a non-linear function, to say it in a mathematical way, in squares, of course not a linear function, it's a square. If you use a non-linear function, then the averages are factored in such fashion. Okay. And then last session we realized if we want to look at speeds, things are fundamentally different than they are for velocities. Where the speed is this positive number which says how fast is the particle no matter in what direction, or in the direction it happens to go. For speed, we needed to figure out at this point, C over here, I have a certain velocity in y direction, and I have a certain velocity in z direction, and then I have also a certain velocity in x direction, and at that point C over here. And then I can figure out what's the probability by looking at g of vx times g of vy and g of vz. But this point C up here is not the only point which has that speed. There are many more points which have that speed, which are all on the sphere shell. If I could draw this around the point C. They all have the same speed. They have different velocity in x and y and z directions, but if I square them each and add them up and take the root out of it, I get the same number, I get the same speed out of it. And so it depends on how far they are. The bigger the speed is, the bigger is the sphere shell, and the more ways are there to set up the speed, the more different velocities in x, y, and z direction I can have in order to get to the same speed. And as a consequence, I need to not just take this product here, I also need to multiply it by 4 pi times the speed squared, which is just the area of that sphere shell. And then I'm getting the distribution here, Maxwell distribution or Maxwell-Boltzmann distribution. Now that looks different, because the sphere shell, the sphere shell over here, the area of the sphere shell goes to 0. If the speed goes to 0, I have for 0 speed the smallest probability, 0. So it goes to 0 as I go to 0. That's much different than here, the normal distribution, the bell curve, which had a value larger than 0 at 0. So here the maximum was directly at 0, and here 0 is kind of a minimum. It's an edge of the definition area. Okay, and then if I'm going to larger speeds, I'll have more. Another thing to realize here is, if I'm at one temperature, say 300 Kelvin, then I know that the average kinetic energy of the particles needs to be 3½ K Boltzmann times T, correct? In order to get that fixed kinetic energy of the particles, I need to have light particles go really fast, because the kinetic energy is 1/2 mv squared. If m is small, then v needs to be big in order to get to that fixed value. Whereas if I have heavier particles, here argon is 10 times heavier than helium. If I have heavy particles, then they need to go slower, so that the 1/2 mv squared still gets to 3½ K Boltzmann times T. So, the lighter a gas particle is, the faster it needs to move. And really, the molar mass is relevant. Helium molar mass is the atomic mass, correct? But for oxygen, the relevant mass would be 32 and not 16, because we have O2 molecules. So they would be almost like argon. And there are lots of ramifications in that. One thing the people in my lab see all the time, if they use hydrogen gas, even lighter than the helium, H2, correct, mass 2, then they have a much better heat conductivity of hydrogen than you would have of air. It can transport heat much faster, hydrogen, because the atoms are moving much faster. They can get much quicker from one side to the other, they can transport heat much quicker. They will also more frequently bounce at other surfaces, and so probably get more likely into reactions. So there are lots of ramifications of this, which are relevant for kinetics, which are relevant for telling us how fast reactions are going to be, and we're going to talk about that in about 3 to 4 weeks. But let me already preface it here. Okay. If I'm having this function here, the Maxwell-Boltzmann distribution, and I'm fixing what I'm having, nitrogen here, and if I look at different temperatures, then at higher temperatures I will have the average being the larger number, because the average of that is always 3½ K Boltzmann times T, and the T is now 1000 Kelvin or 300 Kelvin, so I get the same curve, a little bit fatter and wider to the right. And the curve always needs to be normalized to 1. It's a distribution function, a different distribution function than a normal distribution, but still a distribution function. So the integral over this curve still needs to be 1, and so I'm getting this more squat and wider curve as the temperature is going up. I'm getting more particles at high temperature if I'm at high velocity, if I'm at high temperature, or if I have lighter particles. If I want to figure out how many particles are in an interval between V2 and V3, then I'm integrating over this Maxwell-Boltzmann distribution. Turns out that integral can be done much easier. This factor of V squared allows for partial integration, and then it's actually solvable without the air function. So, now I can look again, what is the most likely, the most probable speed in the Maxwell-Boltzmann distribution? And you'll find the most probable speed in the Maxwell-Boltzmann distribution is about here. It is where the maximum is. If I'm just looking at this left curve here, the 300 Kelvin curve. So this here is the most likely or the most probable, and P will be. And can be calculated. I'm not going to do the math over here, but you can of course see where is the first derivative of this awkward function. You can look where is the first derivative of this one, where is it 0? That gives you where is the maximum, and you find that it is the case at root of 2 k Boltzmann times t over the mass. So the most probable speed scales with the root of the temperature. I double the temperature, I get 1.4 times root 2 the most probable speed. I can also ask what is the average speed, and you see this function is not symmetric. The Gaussian distribution was symmetric, same on the left and on the right. But the Maxwell-Boltzmann distribution is not symmetric. It's wider on the right and it's narrower on the left. So you see that the average speed is a little bit to the right of that. And of course it's not at 0 because all the values are positive over here. So it's not defined for me. Speed is always in the direction the particle is going. So you'll find a value like this. You can also do mass for the average of that, and you'll find it's 8 over pi, not 2, 8 over pi, 8 divided by 3 is a little bit more than 2, correct? So it's a little bit to the right because this was 2, and this is 8 over pi. So it's a little bit to the right. Then you can also ask, what is the RMS speed? And the RMS value is always bigger than the value for a normal average. Just imagine you have an average of 1 and 2. The average, of course, is 1.5, correct? Now I'm taking the squares. 1 square stays 1, 4, 2 squares becomes 4. I'll have 1 plus 4 gives me 5. I need to take the root out of 5, which is 2 point something. So it would be 1.5 for the normal average. It would be 2 point something for the RMS. So the RMS is always big. And you find the RMS is 3. So here it's 2, 8 over pi, now it's 3. Next one I have here is the speed of sound. How fast does the sound travel from me to you? And that is of course again transported by the gas molecules here in the room. The sound is just the vibration in the air density coming from my mouse going to you. It's vibrating how much density we have in the air. And the speed of sound is then 7/5. So there it's 2, there it's 8 pi, here it's 3, here it's 7/5. So it's a little bit on the left-hand side. So it would be like here. That is the speed of sound. But it's also just as much determined by the particles. So the speed of sound depends on the temperature, and the speed of sound depends on the mass of the Earth. Okay. So I think that is what I wanted to say about distribution functions. Are you fine with them now? Do you have any questions about distribution functions? Now, next thing, I wanted to mention the Boltzmann distribution law. And that tells us that if I have particles, the population of particles with the energy E2 and the population of particles with the energy N1, then how many I get out of those is E2 minus E1, the minus sign in front of that difference, over K Boltzmann times T. That comes directly out of the normal distribution. Here in the normal distribution, you see, here you have 1/2 m times v squared, correct? The kinetic energy. Here you have directly the kinetic energy, 1/2 mv squared, correct? So if I were to have one distribution for one energy, 1/2 mv squared, and then for different 1/2 mv squared, and they divide them by each other. This one here would cancel, and I have E of the one minus the other. So that way you are getting the Boltzmann distribution function. So that is often an approximation. And it often is even more approximated, that I say, okay, N2 is really the energy I'm interested in, and I'm asking myself, if I have an energy E2 which is above the ground state, so minus the ground state, 0, then how many particles will be at that energy E2? And I can say, now pretty much all particles will be in the ground state. That's a normal condition in chemistry, all particles are in the ground state, almost all particles in the ground state. So it's really over here, not the total particles here, it's really how many particles are in the ground state, which might be N1 minus N2, but if N2 is a really small number, then it doesn't matter. So the total number of particles is E to the power times E to the power of minus the energy of the state over K Boltzmann times T gives you how many particles have a certain energy. That is one of those things which you have to keep in mind. Whenever you have an approximation, you need to make an approximation in chemistry. How many particles will have a certain energy? How many electrons are in the conduction band and not in the valence band? How many particles are fast enough that when they hit the wood over there can make a reaction with it? How many particles, how many molecules are in a certain vibrational state? How big is the anti-Stokes line environment compared to the Stokes line environment? All those questions ask really how many excited particles are there. And always, if you don't know anything better, you do this. That gives you an approximate answer, not a perfect answer. And why not perfect, we are going to see after the midterm. But it gives you an approximate answer in an easy fashion. And so, Boltzmann distribution law is great for that. It helps a lot. Whenever people tell you something and you don't believe particles have enough energy or it can't happen so fast, this is the back of the envelope way of checking. Because these distribution functions, which have an energy over K Boltzmann times T minus sign in front of it to the power of E, that's everywhere in physics and chemistry. It's everywhere, everywhere, everywhere they come. They always have that shape. That's just the way nature is. Let's look at the atmosphere. That's a picture taken by NASA of Earth. You can see the curvature of Earth and the sun rising behind Earth. And you can see also how thin the atmosphere is. There is not much atmosphere. If you were to paint a billiard ball, it's a tiny, tiny, the thinnest possible you can imagine layer of paint. That paint would be thicker than the atmosphere is compared to Earth. So there is not much atmosphere. Now, and of course in the atmosphere, we have a variation of the pressure. As we go up, there's less and less pressure. And so we can ask ourselves, how much less pressure is there really? And I'd like to do that for a moment. Which is then called the barometric formula. Where I can say that if I were to go just a little bit higher than where I'm right now, that the change in the pressure is, if I were to go a little bit above me, then there would be a little bit less air above me pushing down with its gravity on top of me, correct? So the change of pressure if I go up is just this change of mass of air, which is then above me to the edge of the atmosphere, which isn't very far away, divided by the area I'm looking at. Because this here, dm times the gravitational constant g, that is the force, A is the area, pressure is always force per area. And it's getting less if I'm going up, so hence the minus sign. Okay, so if that is the case, then I just need to figure out what my dm over here is. This change in mass. And this change in mass is the density of the air, rho, times the amount of volume, right? If I'm going a little bit above how much volume, less is air there. And the volume is, of course, the change in height, I'm going up, and the area again. Height times area is again the volume. Okay, now I can plug that in. Then I know that my change in pressure is rho times dH times A times the gravitational constant divided by A. The A cancels. Okay. And I have a minus. Now, next thing is I need to figure out what is my rho, what is my density. Now, density is always mass per volume, correct? And the mass is, of course, the number of moles times the molar mass, still divided by volume. Now you all know PV equals nRT. Now I have an NV over here. I have an NV here, N over V. From this one here, I can also say that N over V equals P over RT. So over here I can say my density here is not N over V, but P over RT. P over RT times the molar mass. And then I can put it in here and say, okay, so my change in pressure over here is minus P times M times G over RT, and I still have my pH. So now, that is a differential equation, correct? I have a P over here and a P over there. So I bring my P over to the other side. I have 1 over P dP equals minus M times G, the gravitational constant, molar mass times gravitational constant, over RT times dH. And I can then integrate that. I can get here the integral, and I say I'll integrate it from height 0 at which I have the pressure 0. So that is ln P minus ln P0. Ln is the integral of 1 over P. And then over here I have minus mg over RT times integral of dH is just h squared. Height minus height 0. Okay, then I can put that on exponentials. On this left side and the right side, I get e to the power of ln(p), which is just p, minus e to the power of ln(p0), which is divided by p0, because minus ln is plus ln of 1 over, so p over p0, and on the right-hand side, I already have e to the power of minus mg height over height 0 divided by RT. And then I just need to bring my starting pressure, the pressure 0 at height 0 over to the other side. And I get that the pressure is the pressure at a height 0 times e to the power of minus mg of the height over height 0 divided by RT. Where the bottom line here is, this is then called the barometric formula. It gives you the pressure in the atmosphere, assuming that you have constant temperature in the atmosphere, which is not a very good approximation, but it's better than no approximation and not knowing it. So the pressure is going down as you're going up because there's less air lining. But the important point here is, mg times the height, the molar mass times the gravitational constant times the height, that is a potential energy, right? And that is here the potential energy. And it's the molar mass, so it's a potential energy for mole of the particles. And you divide it by RT, which is k Boltzmann times T times the Avogadro constant. So it's R if you have a molar thing. So you have again the same thing, which I have in over here for the kinetic energies, for the Boltzmann distribution. It's the energy over kT gives me how many particles are there. Here for the pressure, and the pressure allows us to give density in the distribution of particles in the atmosphere again. It's again the energy over RT. Wherever you can go, in chemistry, in physics, always have distribution functions being this e to the power of minus energy over RT or kT, depending on whether you look for molar particles or a single particle. No matter whether you think the kinetic energies or you think an potential energy of air masses above you or vibrational states or whatever it is, you always get e to the power of minus delta E over k Boltzmann times 2. That's just the way nature is. Nobody can secret. It's just the way it is. So, okay. Before I close, and I might be a little short today, but I don't want to start something really just before the meeting. It's important for you to understand how big atoms are. And sometimes, even if you study chemistry, things like that get lost. So I'm sure you know milli, micro, nano, pico, and then so on. You learned them common sense. The diameter of an atom, all atoms of course are different in size, but depending on which element you have. But the diameter of an atom might be like 1.5 angstroms in the second period, maybe 2.5 angstroms if you go below the second period. Somewhere there. Angstrom is 10 to the minus 10, 0.15 nanometers. So, thickness of your hair, about 10 microns, 10,000 nanometers. So, your hair is about 100,000 atoms across. Size of a atomic molecule. Molecule is 2 atoms. So the bond length, somewhere maybe 1.2 or so, 10 to the minus 10 times 2 gives you 2.5, somewhere thereabouts, angstrom length, okay? 2.5 or so angstrom length for diatomic molecules. Times 4 gives a nanometer. 4 molecules set next to each other gives you nanometer. 10,000 of them gives you the thickness of your hair. just give or take. Cross-section of a atomic molecule. Now things are getting kind of iffy. So maybe we have, say, this 2 is 4, this is 2 over here, and then 2 by 2, so gives you about 4 angstrom squared and cross-section. But if you were to express that in nanometers, of course, or then with 0.04 nanometers, or if you express it in meters, you now have 4 times 10 to the minus 20 meters. Nanometer is 10 to the minus 10, nanometer times nanometer is 10 to the minus 20 meters, right? Or nanometer is 10 to the minus 9, so 10 to the minus 18 would be nanometers. So don't forget that if you make areas of cells on the atomic scale, you get really big exponents because you have a small x times a small y, and so you get really small numbers. You can also say, oh, what's the volume of that diatomic molecules? And you can say 2 by 2 by 2 angstroms would be 8. I calculated here 6 because maybe it's a little bit longer, but not so big in the direction where there's not the bond. So maybe 6 angstroms, give or take. But in meters, that would be now 6 times 10 to the minus 30 cubic meters. So really, really tiny. Nanometers are really tiny distances. Nanoliters are actually not so tiny amounts of volume. It's just because one has a third thing in another. Okay. Now we have PV equals energy all the time. You know it's 22 liters so, for a mole of gas. If you have 22 liters, that is 0.022 cubic meters. And now you divide it by the Avogadro constant, you get a volume of on the order 10 to the minus 26 cubic meters, or maybe 3,650 or so, give or take, cubic angstroms. And we said it's 6, so it's maybe 8, or somewhere thereabouts is the volume of the molecule. So there are not many molecules, correct? In a gas, each molecule has 3,000 something cubic angstroms, but the volume of the molecule itself is only 6 or 8, less than 10 cubic angstroms. So most of the space in this room, which is full of gas, is empty. And so our initial approximation that we have a nearly ideal gas is pretty accurate, isn't it? If I'm looking at the size of the box, so I'm asking here 3,650 cubic angstroms. How big a box is that actually? It's 15 angstroms times 15 angstroms times 15 angstroms. 15 times 15 times 15 is about 3,600. So that's actually, we said a molecule would be like 2.5 angstrom long, and it's a 15 angstrom box, so it's like this compared to that. And then of course also in the other direction. This is the size of the molecule, this is the size of the box in one direction. No, of course it's very small, I'm going to show you some things, but it's about those relationships in size. So yeah, if I'm thinking about volume, the molecule is taking up very little space in that volume. If I'm thinking about the size of boxes, it's actually not so different. It's not even a factor of 10. Now, the molecules, how fast do they move? We looked at all those things, and let's say they move on the order of 500 meters per second. Somewhere thereabouts we have it, right? If I'm going all the way back over here, 500 meters per second would be here. So pretty accurate, right? So they would move on the order of 500 meters per second. That is 10 to the 12 angstroms per second. So if they are 15 angstroms apart from each other, here's one molecule, that's its box, and then the next molecule would be like here, right? Or somewhere in its box. those 15 angstroms, they travel on the order of 1 picosecond, 10 to the minus 12 seconds. So 10 to the 12th times they travel from their own box into the adjacent box each second. So if you assume what fraction of the box does a molecule take in terms of area of the box, then you can say it's about 100th or so of that area of that box. It's somewhere in the depths the molecule is. So about 1/100th of the time, the molecule is traveling from its box to its neighbor's box. About 1/100th of the time, it will hit the molecule. So it will hit on the order of 0.1 nanosecond, right? Every 0.1 nanosecond, on the order of 10 to the 10 times per second, a molecule will hit its nearest neighbor, or one neighbor, in the gas phase. That's an awful frequent times, isn't it? 10 to the 10th time. 10 billion times per second. You can also ask yourself, how far will the molecule go before it will hit it? And that's about 100 of its boxes. Every 100th time or so it's going to hit it. So it's on the order of 15 angstroms times 100. It's on the order of a micrometer. So if the molecule were to travel 1/10 of the thickness of your hair, it will probably hit already another particle. And it will do so 10 billion times each second. So that is what's going on in the gas surrounding. Does it make sense? Always keep those kind of approximations in your mind if you think about what molecules do. Because it's important to realize how reactions in the gas phase proceed. Lastly, I have one more slide. And that slide here is, now going back to the very first slide we had in the beginning. And in the very first slide which we had in the beginning, we said, oh, it's 1/2 K Boltzmann times T per degree of freedom. So what's the heat capacity of the molecule? And you'll find it is 3/2 KT for all directions. So it's 1.5. So 1.5 R is the heat capacity for helium, for neon, for argon, for krypton, for xenon, for all the noble gases. The heat capacity is indeed 1.5. These are measured values. They are not calculated values. If you measure the heat capacity of gases, they are just 3/2, 1.5, and then for mole, not R, but K, but R, done. It's pretty accurate what we can do. So, with that, let's have a look.